Hello everyone, welcome to the channel. In this series, I will be solving all the questions in the exercises of material selection and design by Mike Ashby. So, in this particular video, I'll be solving exercise 5.1 to 5.10. Here we are going to cover introduction to Ashby plots, how to familiarize yourself with the Ashby plot and how to use the Ashby plot. So, take a second, pause the question and read the question. So if you look at the question, you can see that it says a material that is made from copper alloys. The material is made from a copper alloy, which is what? Brass, made up of what? Copper and zinc. And we are trying to replace this material with another material. So they said use this chart, use this density over density and Young's modulus chart to find materials that are stiffer than what? Copper alloys. So we are looking for metals, only metals that have the same shape, but that are stiffer than copper alloys. So we don't care. So if you look at the chart over here, we don't care about density. All we are looking for what is the Young's modulus, the ones that have what? Higher Young's modulus. So if you look at over here, we can see elastomers, foams, polymers, non-technical ceramics, natural ceramics, composites, technical ceramics, and metals. So we care about metals that have what? Higher Young's modulus than what? Copper alloys. So if you look at the metal chart, can find copper alloys just above it. So this is copper alloys. So I can just shade copper alloys to make it what? Visible. Let me get rid of this. Then I can just shade copper alloys to make copper alloys a little bit visible. So now all we have to do is get our ruler. You get your ruler, place it at 0 degrees and just place it just above copper alloys. So I'm placing it just above copper alloys, and we are looking for metals, only metals. So you can see everything here in the yellow is technical ceramics, and the ones in red is what? Metals. They are looking for just metals that have what? Higher Young's modulus than what? Copper alloys. So if you look at it here, all we have is what? This. So let's just draw a line. Let's draw a line first that crosses every other thing out. Then we remove our ruler. So we are looking for things that have what? Higher Young's modulus. So first we have this, which are 1, tungsten alloys. 2, we have what? Nickel alloys. And 3, we have what? Steels. So if you look at this, every other metal or metal alloy is below the line. So they have what? Lower Young's modulus, or the same Young's modulus as what? Copper alloys. So these are the materials that we can replace what? Copper alloys with. Thank you very much. We are moving on to the next question. Okay, for question 5.2, take a second to read the question. Okay, the question says use this chart, Young's modulus over density, to identify materials with what? Both a modulus greater than what? 50 gigapascal and a density less than 2000 kilogram per meter cube. So we are looking for a material that is stiff but is light. So a light and stiff material. So we are looking for higher than 50 MPa, gigapascal. So we just get our ruler. So if you look at this scale, the scale is in what? Logarithm. Is in logarithm scale. So we are looking for what? 50 gigapascal. Get your ruler. Look for what? 50 gigapascal. So this is 10, 20. So this is 10. This is 20. This is 30. This is 40. And this is what? 50. So all we have to do is draw a line. So the same thing. We do the same thing for less than 2000 watts kilogram per meter cube. So we turn our ruler all the way to the horizontal at 90 degrees, and we are looking for a material with watts less than 2000 watts gigapascal. So we are looking for less than 2000 gigapascal. So this is 1000 and this is what? 2000. So at 90 degrees, less than 2000 watt gigapascal. So we draw a line. So now that we have our line, we can now increase this. Look for material. So everything here, we are looking for greater than what? Greater than 50 gigapascal. So everything here is out of the question. And we are looking for materials with what? Less than what? 2000 gigapascal. So everything here is out of the question. So our best materials with both properties are what? CFRP. If you look at here, we have what? CFRP, carbon fiber reinforced polymer. So CFRP, and the next one is, if you look at here, which other material that passed our selection? So technically, we have just carbon fiber reinforced plastics as our best material that passed the boat selection. So this is the material that we are selecting for this particular application. So for question 5.3, take a second to read the question. So they told us to use this chart to find materials that are stiffer and less dense than steel. So A says like what? Let us find metals, only metals that are stiffer and less dense than steel. So first we have to find what? Steel in our chart. So if you come here, you can see steel. Steel is very small. So this is steel. This is steel. So this is very small in our chart. So we just make a mark on steel. Now that we have a mark on steel, we can now try and find metals that are what? Stiffer and less dense than steel, right? So all we have once we have this, we bring out our ruler and look for materials are less dense. If they are less dense, they should be just behind steel. So we draw a line. So and if they are stiffer, we change our ruler to 0 degrees. And draw a line. So now that we have this, we are looking for material that are what? Stiffer. So everything that is below this line is not accepted, especially metals. We are looking for just metals, right? And we are looking for metals that are what? Less dense. So everything here as well is not correct. So if you look at here, you can look at the metal envelope. There are no metals that are stiffer and less dense than steel. So A, for A, no metals. Then for B, it says not just metals, any material that are both stiffer and less dense than steel. So since we have here, we are looking for any material at all. So you can see most materials that are stiffer and less dense than steel are what? Technical ceramics. So for B, our answer is what? So first we have what? Alumina, Al2O3. And we have what? Silicon carbide. We have what? SiC, silicon carbide. Then we have what? Silicon nitride, SiC3 and 4. Then which other material? We have boron carbide. Then we have, so that's all the materials. So all the materials that are here are the materials that are what? Stiffer and less dense than what? Steel. If you have any question, drop it in the comments. Let's move on to the next one. Okay guys, for question 5.4, take a second to look at the question. So here it is telling us to identify metals with both Young's modulus greater than what? 100 gigapascal, and the relationship between Young's modulus and density should be greater than 0.02 gigapascal per kilogram per meter cube. So first, for 100 gigapascal, we have to find materials with Young's modulus above what? 100 gigapascal. So we get our ruler. So at 100 gigapascal, so this is it right here. Let's just stick this up. We just draw a line for 100 gigapascal. Then, so after now we have materials with 100 gigapascal, we can now draw the line for what? Young's modulus against what? Density. So we look for 2 points in the graph that will give us what? E over P of 0.02. So the relationship here is what? E divided by P, density, or rho, is equals to 0.02. So let's say first, let's take what? Density as what? 100. So when density is 100, E will now be equals to 100 times 0.02, which will give us what? 2. So that will be our first point. Our second point, let's say when density is what? 10,000. So when density is 10,000, our E will be 10,000 times 0.02, which will now be equals to what? 200. So we'll now look for these points in the graph. So first point, 100 and what? 2. So when Young's density is 100, our Young's modulus is 2. So we get our ruler as well. Same thing. Get your ruler. So at 100 and 2, so this is 1 and this is what? 2. You draw your point just right there as the first point. So the next one is when density is what? 10,000 and our Young's modulus is what? 200. So at 1,000, so this is 1,000, and at go to 200. So this is 100 and this is what? 200. We now draw our second line. So we know all we have to do now is to join the two lines together to make a slope. So we are joining this and this to make a slope. So this point and this point. So now that we have joined it, we'll just draw a line to make the slope. So this is our relationship. So this is now our relationship. We are looking for only metals. So we have to what? Cancel whatever that is below here. is not available, and whatever is below here is not available, and whatever is here is not available. So we are looking for only metals. Only metals. So our answer is the metals are, if you look at here, the metals you have what here is what? 1, nickel alloys. 2, you have steels. And 3, we have what? You can see a little bit of what? Titanium alloys are there. So 3, we have what? Titanium alloys. So that's our answer for this question. Let's move on to the... Okay guys, take a second to look at this question 5.5. So for this question, we are trying to find materials with what? Higher Young's modulus greater than what? 100 gigapascal. And we are looking for also materials with a higher relationship of E raised to the power 1 over 3 divided by what? Density of what? 0.03. So they are reminding us also that the relationship between E raised to the power 1 over 3 divided by density is given by this formula. The log of E is equals to 3 log density plus 3 log what? M, which is what? The material index. So they're telling us to use this relationship to find what? The best material. So first, let us solve for what? E greater than what? 100 gigapascal. So for E greater than 100 gigapascal, we'll get our ruler and look for materials with a higher Young's modulus than 100 what? Gigapascal. So now that we have this, we'll draw a line greater than what? 100 gigapascal. Then we are looking for the relationship of what? E raised to the power what? 1 over 3 divided by what? Density is equals to what? 0.003. That's what we are looking for. So what? First, we can say, we can use 2 points to draw our curve. So at what? 100, at 100, density of what? 100. So when density is 100, E will now be equals to 100 times 0.003 all raised to power 3. Then our E will be equals to what? 0.027. So that's the first one. So when E is now, when density is now equals to what? 1000. So when density is 1000 times 0.003 all raised to power 3. So our value of E will now be equals to what? 27. So with these 2 points, we can plot the next line. So we'll now bring out our ruler again. So when E is 100, when density is 100, our E is what? 0.007. So 0.007. So this is 0.00, this is 0.2, this is 0.02, this is 0.02, and this is what? 0.027. So somewhere around here should be 0.027. So we now draw a line at what? 100. We now draw our first point. Then the next point is when E is what? 1000. So when E is 1000, which is here, and our next line is what? When density is 1000, our E is what? 27. So we'll go to 27. And when E is 1000, so this is 10, this is 20, so 27 should be somewhere here. So we are looking for at 1000, our E is what? Somewhere here. So now that we have the 2 points, these 2 points, we can now draw a line and get our ruler again and draw a line that passes through these 2 points. So now that we have this, we can now draw a line, and we have to now, okay, once we have our line position, we can now draw our line. So now once we draw a line, we know that everything below this line is not accepted, and anything below this line is not accepted. So based on that, the only 2 materials that passed our selection, you can see small part of this material, which is boron carbide, and small part of this material, which is what? CFROP. So the 2 materials, one is what? Boron carbide, which is B4C. Then the second material is what? Carbon fiber reinforced what? Plastic. So these are the 2 materials that were passed our selection. So guys, take a second to look at this question. So in this question, they're telling us to establish whether woods, all types of woods, have what? Higher specific stiffness with respect to what? Epoxy. If they have what? Higher specific stiffness compared to what? Epoxy. So here we can see there are 2 types of wood. If you look at our graph carefully, where we see natural materials, you can see 2 types of wood. We have one, which is what? The parallel wood grain. And we have another type of wood here, which is what? the perpendicular wood grain. Then we have what our material, what epoxy over here. So we are comparing if these two would have a greater E over density value greater than what epoxy. So there are two ways to do this. You can either do this by manual calculation, or you can do this by, you can see the relationship between E over P have already been drawn here on this curve, which is what E over density, which is this one. We can either move this up, and every material above this line, when we move it up, is have a greater E over P value, and every material below this line have what a lower E over P value. So first we have to do this by manual calculation, just to show you how it works manually. By manual calculation, then we can now use this line in order to do the selection. Okay, first we have three materials that we are comparing. First is what parallel grain wood. The next one is what perpendicular grain wood, and the next one is what epoxy. So we are trying to calculate their what E over P value. So for density for parallel grain wood, so here you can see wood has what a range of values. So over here we can see wood has what a range of values based on this what big circle. Based on this big circle, you can see that wood has what a range of values. Even this one has what a range of values, and epoxy have what a range of values. So what we have to do is what take our ruler and measure. Take our ruler and measure like the higher boundaries, the higher limits, in order to make what this calculation. Just take our ruler and measure what higher limits in order to make this calculation. So that's what we are going to do. So we'll get our ruler. First we will measure what their Young's modulus for all the material. So we go to parallel grain wood, which is this, and we are looking for what the higher limits of what parallel grain wood, say somewhere around here. And we say for parallel grain wood, what the value of E, we are looking for E over what density, which is what the value of E is what 20 gigapascal. So for perpendicular grain wood, which is this one, which is this material over here, which is this material over here, we are looking for the higher limit for Young's modulus, which is around 3.5. So which is around what 3.5, which is for this we have what 3.5. This is equals to E divided by density, which is equals to 3.5 gigapascal divided by, so the last one we are looking for epoxy. So we'll go to epoxy, find the E of epoxy, the higher value of E of epoxy. Let's say 3.2 is around 3.2. So you can see the E of epoxy is what is equals to E divided by density is equals to what 3.2 gigapascal. So now we'll look for the density of each of these materials. So we'll take our ruler, bend it all the way to the vertical position, and look for what higher limit as well. So for parallel grain wood, we are looking for what the higher limit of this, which is what, let's go this way so it will be easier to visualize this way. For this one we have what 100, or we can do it either way. So we have what 100, 200, 300, 400, 500, 600, 700, 800. So our value for density is what 800 kilogram. Oh sorry, that's for, so even though you can see both our parallel grain wood and what perpendicular grain wood has what the same what density, so 800 kilogram per meter cube. Also this one has what 800 kilogram per meter cube. Then for our epoxy, we now change this all the way to epoxy, look for the higher limit of epoxy and leave it there. On there. So if you do this calculation, if you break down the logarithm scale of this, you can see that this has what a value of what 1200 or 1250, something like that, around that range. So 1250 kilogram per meter cube. So now we can now manually calculate these values to see what our answer is. So for this one has to be, for wood, parallel grain wood, we have what 0.025, which is equals to 225 times 10 raised to power what minus 3. So if you punch this one out, you have what 4.38 times 10 raised to power what minus 3. Then for this one you have what 2.56 times 10 raised to power what minus 3. So you can see between these three values, you can see that parallel grain wood has what a far higher Young's modulus divided by density value, which when compared to perpendicular grain wood and epoxy. So this parallel grain wood is so much more stiffer have higher specific stiffness when compared to these two materials, but these two materials have what similar. So you can see 4.3. Perpendicular grain wood still has what a little bit higher than epoxy, but they are almost in the same range when compared to parallel grain wood, which also has way higher specific stiffness. So this is the first way of doing this. The second way of doing this is taking our ruler. We'll take our ruler and try to guide this line. So you can see the line over here, the line of Young's modulus over density, which is what is asked of us in this question. So we are trying to find the material with greater E over P. So any material that is above this line has higher E over P, and every material below this line have a lower E over P value. So we just have to place our ruler just exactly at this line. Once you have your angle set up, you can now move this line up. So as you're moving up, any material greater, so now I'm here, all this material here have greater E over P value than any material here. So that's what we're going to do to compare wood and epoxy. So we are going all the way. Okay, let me just mark out epoxy so it will be able for you to visualize. So this is epoxy, and this is wood. This is perpendicular wood, and this is parallel grain wood. So now we have these three materials. We can now move our ruler. We changed the E over P value, so make sure that our angle stays the same. So now we have our angle. All we have to do is move this line off. So as you're moving up, you can see that at a point these two lie on the same plane. Parallel grain wood and epoxy lie on the same line. So we can say that they are almost similar, have almost similar specific stiffness. But if you go up, if you're moving this up, it gets to a point that's the upper limit, whereby parallel grain wood has slightly higher specific stiffness compared to epoxy. But if you now go up all the way to this point, you can see that both these materials, both parallel grain wood, both perpendicular grain wood and epoxy, are all covered. So the best material over here is parallel grain wood, which has way higher specific stiffness compared to perpendicular wood and epoxy. So this is another way to do this, and we are going to be using this way in other next questions that we are going to solve. So let's move on to question 5. Question 5.7. So this question is similar to question 4.6 that we just solved. So they're asking whether titanium alloys have a higher or lower specific stiffness when compared to density. So the relationship we are looking at here is the strength, the failure strength of failure strength divided by density. That's the relationship we are looking at here. And we can see in the graph they have already provided us with different lines of different relationship. So here we can see stress over density. Here we can see stress raised to the power 2 over 3 with respect to density over density. Then here we can see stress raised to the power 1 over 2 divided by density. So this is the line that we are caring about. So this is the line that we want. This is the line that we want to use and find our relationship. So all we have to do is take our ruler, place it on this line. So you can manually calculate this as well. You can manually calculate this, but this is the best way to do this. This is the most efficient way to do this. You can manually calculate this as well, like I said. So all you have to do is place this on this line. So once you place it on this line, so this is 27 degrees, all you have to do is move your ruler up. So since we have this line, we have to move our ruler up. So move this ruler all the way. So let us find the two materials that we're looking for, which is titanium alloys. So you go to metals. These are titanium alloys. So everything here is titanium alloys. And steel. This is steel. And let's say everything here. So now that you have this line, all you have to do is move this relationship up. So as you're going up, you're cutting off materials that have lower stress over density. So as you're going up and you're going up and you're going up to this point. Up to this point, you can see that at this point, both steels here, and titanium alloys have similar stress over density. But as you keep on going up, you get to a point that only titanium alloys is available. So above this point, it gets to a point where to move this up all the way to the point where you have only titanium alloys that are available. So titanium alloys have higher specific stiffness than steel. So for this question, take a second to pause the question and look at the question. Here we are told to find materials with Young's modulus greater than 10 gigapascals. So E should be greater than 10 gigapascals. And also we are looking for materials with higher strength, higher fracture strength of greater or equal to 1000 MPa. So all we have to do is take our ruler and find those points. So for 100 gigapascal, for 100 gigapascal, we take a ruler and place it at what? 100 gigapascal. Just at 100 gigapascal. So once we place it, we can now draw our lines. So what we have to do, once we place our ruler, we can now draw our lines at what? Next, we'll now draw a line for what? 1000 what? MPa. So at 1000 MPa, we'll take our line and draw it for 1000 MPa. Okay, just split. So next, we'll now draw a line for 1000 MPa, which is somewhere here. Once you draw a line at 1000 MPa, so everything here, so greater than 10 gigapascal, so everything here is out of the selection, and everything less than 1000 MPa, everything over here is out of the selection. So our materials, you can see the only materials that passed here, if we zoom in, the only materials that passed here are what? Steel. So high strength steel, some steels over here, you can see here, high strength steel passed, and also the only material that passed, you can see here, are titanium alloys. So some parts of titanium alloys passed this selection. So titanium alloys and what? High strength steels are the ones that would pass this selection. Also, you can see CFRP. You can see the large circle for CFRP, carbon fiber reinforced plastic. So some parts of what? CFRP also what? Pass this selection. So we have three materials that pass this selection: titanium alloys, steels, and CFRP. So if you come back here, you can see that what? The materials that are here are what? High strength steel, 1. High strength steels, 2. You have what? Carbon fiber reinforced plastic, and we have 3. We have what? The third one, we have what? Titanium what? Alloys. So these are the three materials that would pass our what? Selection. So guys, take a second to look at this question. So we are trying to figure out if the K1C of these three polymers, which are ABS, polystyrene, and what? Polycarbonate, if they have what? A greater K1C than what? Alumina, Al2O3. We are trying to see if this is greater or less than this of Al2O3. Also, we are also trying to look for if their G1C, the G1C is equals to what? K1C all raised to power 2 divided by their Young's modulus, if it is greater for these three polymers or for what? Alumina. So these are the two things we are looking for. This and what? Just K1C. So these are the two things we are looking at. If we go to our table, our graph, we can try and figure out these three polymers. The three polymers we are looking at is what? ABS. So ABS, let's just draw a round circle around the circle of ABS. So it's gonna be easy to what? Visualize. So this one is what? ABS. Then for polycarbonate, we have polycarbonate, which is this small one over here, which is what? Polycarbonate. Then for the last one, which is what? Polystyrene. This is polystyrene. So we just draw a circle around what? Polystyrene. So we have our three polymers. Then we have what? Alumina, which is this one. We draw a circle around alumina. So we have our three polymers and we have what? Alumina. And we're trying to figure out what? Their K1C. And this is K1C. So if you're going up this graph, you have what? A higher what? K1C. So all we have to do is what? Take our ruler. We take a ruler and change it to what? 0 degrees. And we're trying to measure what? K1C. So first, you can see when you get over here, you can see that these three materials, we have what? Polycarbonates and ABS and alumina have what? Higher K1C than what? Polystyrene. Then you now move your ruler up. As you're moving up, you get to a point whereby what? Alumina and polycarbonates have what? Higher what? K1C than what? ABS. Then if you move this up a little bit as well, you can see that this is now what? Have what? Similar what? K1C values. So here you can write that for K1C. So here you can see, let me delete this. Let me delete this one as well. Let me delete all these ones as well. Just clean it up. So here you can see that for K1C, ABS, polycarbonate and alumina, Al2O3 So you can say ABS, PC, alumina has greater K1C than what? Polycarbonate than polystyrene. Then also polycarbonate and what? Alumina has what? Greater K1C than what? ABS. Also, you can now say that ABS and can now say that what? Can now say that what? Polycarbonate and what? Alumina has what? Almost similar what? K1C values. That's what you now see. Has what? Similar what? K1C values. So that's it. That's it for K1C. That's that for K1C. Then we'll now move on to what? We'll now move on to what? G1C, which is G1C, which is what? The G1C that we have is what? The G1C that we're looking for is what? K1C raised to the power 2 divided by what? E. That's what we are looking for. So like I said in other questions, so this is the line that we are trying to use to compare. So this is the line that we are looking at what here. This is what? K1C over E. This is the line. So any material below this line has a lower K1C over E, and any material above this line have a greater K1C over E. All we have to do is what? Get our ruler and place it on this line. You place it on this line. Once you place it on this line, you can now move down. So as you're moving down, so every material here has a higher K1C than every material here. So you're moving down, you get to a point that what? You get here to a point that what? PC, that's polycarbonate. Polycarbonate is now greater than what? All other material. All material. Then you now move down all the way where you get to a point. Then you see that ABS has a greater K1C value than both alumina Al2O3 and what? Polystyrene. Then if you're moving down all the way down, you now get to this point and you see that only thing that's showing here, you see that polystyrene have what? Greater what? K1C squared over E greater than the what? Alumina 2O3. And if you now move down, you can now get towards alumina. So this is how it is arranged. PC, polycarbonate, is greater than all of them. ABS has a greater K1C squared over E value greater than alumina and polystyrene has a greater what? K1C squared over E greater than what? Alumina. So all these polymer material what? Has what? A higher what? Toughness when compared to what? Alumina. So that's the answer for what? Question 9. So guys, take a second to look at this question. So this question is talking about finding the fracture toughness and finding materials that have what? Higher K1C value, higher fracture toughness than 100. Then they are telling us to find what? Materials that have what? Higher toughness, which is G1C, which is what? K1C squared over E, greater than what? 10 kilojoule per meter cube, sorry. So that's what they are trying to find out, let us know. So first, we are going to look for what? Materials that have what? Higher K1C values than what? 100 megapascal. So when we do it, we just look for materials. We take our ruler, position it as what? 90 degrees or 0 degrees, sorry. So now we have our material, our line at 0 degrees. We can now rule our line at what? 0 degrees, right? Then the next one is what we are trying to do is find the materials that have what? K1C value. So we are looking for what? K1C squared divided by Young's modulus, which is equals to what? 100, which is equals to 10, sorry. So what we're trying to do, we are trying to find 2 points that we can draw this line from. So let's say when K1C is what? 1000. So when Young's modulus E is 1000, then K1C will be equals to 10 times what? 1000 all raised to the power what? 1 over 2. So K1C when Young's modulus is equals to 1000 is given to us as what? 100. So 100. So also for K1C, when Young's modulus, we'll now take another point when Young's modulus is equals to 1. So when Young's modulus is equals to 1, we'll have what? 10 times 1 or raised to power 1 over 2. Then our K1C value is now equals to what? Square root of 10 is equals to what? 3.16. So we'll now find these 2 points with our ruler. So to bring out our ruler again, so we are looking for 2 points. First, when K1C is equals to what? 100, and this is equals to what? 1000. So when this is equals to 100, so same point. So when K1C is equals to what? 100. So this is the point that we are looking for when K1C is equals to 100. So there is no even need. We already have a line. So this is the line, the point we are looking for. So the next one we are looking for what? When K1C is equals to what? 3.16. So at 3.16, the value of what? Young's modulus is equals to what? 1. So at 1, so this is line for 1 and what? 3.16. So this is 1, this is 1 for Young's modulus, and 3.16, this is 2, this is 3, so it's almost what? 3.3. So we are looking for this point. So these are the 2 points that we are looking for. Since we have the 2 points, now we can now draw our line. We'll position this just. So once we have this position, we can now draw a line. So now that we have our line, we know that every material below this line is not part of the selection, and every material below this line is not part of the selection. So our best material that we can see here, we can see what? Some part of what? Nickel alloys that are here. You can see some part of nickel alloys. So the materials that we have were 1, nickel alloys. So the next one we have what? Some steel. So steel. So you have 1 nickel alloys. The next one that you have what? Is titanium alloys. So if you see here, you can see some of what? Titanium alloys that passed the selection too. You have what? Titanium alloys. And you can see the long value of steel, how long steels are. So this is part of what? Steel. So the next one here is what? 3 steels, high strength what? Steels. So these are the materials. So these 3 materials are the best materials for this selection when you have this selection in play. So thank you guys for watching. In the next video, we'll start from what? Question E511. So 5.11 is what we are starting from the next video. Thank you very much. If you have questions, don't forget to leave them in the comments.